All right, welcome everyone again to Neuro-Symbolic Wednesdays. Let me just give my usual introduction while we're waiting for folks to join. I guess I should make this bigger. One sec. Okay, is that full screen? All right, so the usual ways to join, but if you haven't seen these before, you can take a snapshot. We have many avenues by which you can interact with us, including the Centaur AI Institute website. So, and many ways to work with us in projects that cover many, if not most, topics within Neuro-Symbolic AI, including theoretical topics for the mathematicians out there, and systems topics. All right, and how do you work with us? You just email me and start. There's a match. Just jump into meetings. We have this system we're starting to put together and design. So, looking for anyone interested in that. We also have something new. So, and the details will be on this channel on Discord. Okay, BYOP. It was hard to find a reference to bring your own booze that's in Art Deco style. So we have this picture thanks to Joe. But the idea is bring your project, your open source Neuro-Symbolic AI project. And if you want, we'll host it. And the advantage to you will be much more publicity, much more engagement from the community. Okay, so if you're interested in this, also, if it's a really good project we like, it may even result in a tutorial in the summer school coming up, which I'll mention, and so on. And we will rally the community to find developers who might be interested. We have a bunch of developers and researchers interested in just helping out on projects. So let us know about your project. And if you want to make it official, we may be able to get you help. Okay, so we'll be talking more about this, but instructions will appear on this channel, BYOP, bring your own project, okay? On Discord. So we're hiring, if you're a startup, we're giving startups slots to advertise yourself. This is like, really just pitch yourself. Doesn't have to be, I know in the past, startups have been shy because they see the, I've been told, intimidating talks we sometimes host by bigwigs and so on. So doesn't have to be ultra technical to reveal your secret sauce. If you're a serious Neuro-Symbolic AI startup, then let us know. And you can just pitch your self. Okay. Volunteers, we have a whole bunch of ways to volunteer, including helping us curate. You may have guessed, it's a lot of work to curate. There's a lot more Neuro-Symbolic AI work now, and it's a lot of work to curate that and find papers across all conferences, basically. So if you want to, but it's also fun. You learn stuff. So if you want to get involved in that in particular, we're looking for folks there. Okay. A reminder about our format now. Total 1 hour, 30 or 40 minutes presentation, the rest Q&A, and then ideally, Yuheng, you jump on Discord afterward.
Yeah.
And the remaining questions.
Mm-hmm.
If you can, reminder about the summer school. I guess, Joe, you couldn't find an Art Deco summer school. So, we August 6th and 7th. Mark your calendar. Actually, even better, sign up and you'll get reminders on Luma. Okay, and more info will be coming. Of course, expect the usual lots of really top-notch speakers and really excellent curated sample of work going on. We think is impactful. Okay. All right, and now Yuheng will talk about theory of mind reasoning, which I'm excited about in general, that topic. And we'll learn more about it today. Yuheng is at Stanford and presenting a paper that was in EMNLP, and you can check out his work here. All right, take a snapshot of this if you want. You can also put this out on Discord. And you can ask questions through multiple avenues, as usual. All right, and coming up next week, deep arguing. Okay, we may do some of that today. The Q&A. All right, take it away, Yuheng.
Hey. Okay, so can you hear me?
Yes, we can.
Okay. Okay. Can you see screen?
Yes.
Okay, thank you. Okay, thank you, Alexander. Thank you, Olga, for arranging this event. Thank you so much for the invitation. And today I'm going to talk about inference-time scaling for self-mind reasoning with dynamic epistemic logic. Okay, so we're going to talk about what is self-mind, how LLM perform in self-mind tasks, and what's existing research gap, and how we use dynamic epistemic logic to address this. We'll talk about our DL self-mind framework, and we'll talk about our results, and we'll discuss about this kind of result and future work. Okay, so first of all, let's talk about self-mind and AIMs. Okay, self-mind is the ability to attribute mental states like your beliefs, your desire, intentions to others, and to understand that others can hold beliefs different from one's own. Okay, so here's a classic example. This example is called unexpected transfer. Okay, assume we are a little child and we are going to take a task. And this task is like that. Alice and Bob are in the living room. A pen is on the table. Alice leaves. Bob moves the pen to a box. Question, where does Alice think the pen is? So as a little child, we need to have some reasoning process. Okay, so the answer should be Alice think the pen is on the table. The reason is the child should be aware that after Alice leaves, Alice doesn't know what happened after that, right? So Alice doesn't know that Bob moved this pen to the box, so Alice still seeing the pen on the table. Okay, so this is a classic self-mind example, and it's called unexpected transfer. Okay, so we have many theory of mind tasks, and now we have two examples. One is unexpected transfer. So it's about an object is moved without protagonist knowledge. And the question is, oh, where will the protagonist look for it? Right, so this is unexpected transfer. We also have another example. This is called unexpected contents. So the example like that, a box labeled chocolate, but actually it contains popcorn. And Sam only read the label. What does Sam believe is inside? The answer should be chocolate, because this guy only see the label, and the label is chocolate. Okay. So both probe the same skill. These are two different false belief tasks. It's like separating reality from another agent's outdated belief. Okay, so this is classic false belief tasks. Okay, so one interesting question is, do LLMs have this kind of theory of mind task? Because this kind of task is used for children's early development assessment, and it's really interesting to assess whether LLM has this kind of capability. And recent evaluations suggest that LLM appear to pass many theory of mind tests. GPT-4 matches adult humans on false belief and erroneous tasks, and smaller and older model lag substantially. So it seems that this kind of performance also follows a scaling law that small models fail dramatically. And actually, model often gets the final answer without coherent reasoning, right? Because this is kind of fill the blank task. You just need to fill the final result. And it's more like kind of multi-choice selection, right? It can be in the box, it can be on the table. Sometimes this model just make a guess, and luckily they're correct. Okay, so it seems that LM has theory of mind is not that good. And actually, theory of mind is extremely important for LMs, right? Because if LM has this kind of theory of mind, that means theory of mind can understand user intent under ambiguity, right? LM can anticipate what the collaborator knows or does not know. And this is useful for avoiding misinformation, manipulation, and miscoordination. That means theory of mind is extremely important for socially aware agents, right? And in real-world deployment, we use edge agents, right? It's on our phones, on kind of robots, it's on device assistants, right? They run small models. And seems that these models can pass today's theory of mind tasks. Okay, so now we're going to talk about LM for theory of mind, and there's a big problem called verifiability problem. Okay, so the first point I will talk about this in last page, like powerful model, GPT-4, Cloud, DeepSeek V3. Now it's not GPT-4, it's GPT-5. Okay, so we finished it last year, so it's GPT-4. This kind of powerful model perform well on theory of mind benchmarks like HiTom and the benchmark proposed by Michael Kosinski last year. And small models like Queen 3, Llama, there's no more Llama today, so now we have Queen 3.5. Okay, but basically this kind of edge deployment scale small models does not have a powerful theory of mind reasoning capability, right? So edge agents cannot afford a 200 billion parameter models, but they interact most closely with users, right? So we hope this kind of small models have this kind of theory of mind reasoning capability. Okay, so this is the first problem. And the second problem is about evaluation, right? So current theory of mind evaluation compare only the final answer to the ground truth, right? So correct answer can come from guessing, and wrong intermediate beliefs can still yield right final answers. And there's no way to tell the difference. It's a guess or it's a true reasoning, right? And of course, we hope this small LM can do a kind of verifiable reasoning instead of just a guess. Otherwise, it's not auditable. So yeah, so this is the second problem is about evaluations unverifiable at this stage. Okay, so the research question is quite simple. How can small LM perform self-mind reasoning that is verifiable step by step, right? And we believe this is extremely important for current socially aware agent deployment. And if we want this reasoning process to be verifiable, we can start with one old school philosophy concept called process reliabilism. Okay, so in this concept, a reasoning process is reliable if its intermediate steps on each choose tracking, not just its final output. So if we want to have a verifiable self-mind reasoning system, that means a sequence of belief states whose update we can independently check. We need to check off this sequence of belief states instead of just the final answer. Okay. Okay, so now we're going to talk about how can we use dynamic epistemic logic to enable this verifiable self-mind reasoning. Okay, so first of all, we need to form a logic system for beliefs, and actually, we are not the first to do that. This is a really old school story. Can date back to like 1950s, 60s, right? So Hintke is one of the pioneers in this topic. And in his work, he said, oh, to know what John knows is to know the words that are compatible with his belief and to know which ones are not. So if we want to have verifiable self-mind reasoning, we need to define several concepts, right? So here we need to define several concepts like words and what's beliefs, what's compatible words, something like that, right? So now belief become a set of is kind of set theoretic object, and the belief is the worst one considered possible, right? And belief can change, right? Belief change become and now belief change become a computable operation on these sets, right? So now we need to introduce what is this kind of concept, was words, was belief, right? And basically, this is a really old school question, right? And this can trace back to Frege, Rousseau, about formal language, formal semantics, right? So these are foundations for the computable logic of belief. And later is Hintke and Crick, we talk about model logic, model epistemic logic, right? So now they talk about semantic over possible words and accessibility relations. We're going to talk about this later. And after that, there's some work on dynamic epistemic logic, right? In this framework, they introduce new concepts like events model and product update operator. In that case, belief can evolve on their actions. Right? So this is dynamic epistemic logic. And later, some people find, oh, actually, we can use this dynamic epistemic logic to illustrate false belief tags for state of mind. Right? So, I mean, we're not the first to introduce this kind of concept. We just reuse this kind of old school philosophy concept and to have some, to make it work in LM reasoning. Yeah. So so in Bollander's work in 2014, he proposed that actually this kind of Sally-Annie self-mind test can be formalized into dynamic epistemic logic. Yeah, so this is the direct concept ancestor of this work. Okay, so now let's introduce the epistemic language. Right? Okay, so first thing is we need to define several concepts. The first concept is atomic propositions, P. Right? So P is basic facts about the world, and now we also have a finite set of agents, A. Okay, so what's basic fact about the world, right? So what's the proposition, right? One example is chocolate is in the drawer. So this is an atomic fact. So this is a P, right? And now we can we can have some syntax. We can compose this kind of atomic facts, right? We can have P itself. We can have negative P. We can have two atomic fact combined together. We can have Bi phi. So let's say this Bi is specific applied to this kind of epistemic model logic, right? So Bi phi means agent I believes phi, right? So now we can represent lots of beliefs directly, right? For example, be Mary, be Alice, chocolate in table means, oh, Mary believes that Alice believes the chocolate is on the table, right? So so we can change this part, right? So if we change this is not epistemic model logic, and we have lots of other model logic, right? So now we just trying to show an example in epistemic logic. Okay, so this is atomic facts. This is how we define P, right? And now we can define word, and word W is a complete choose assignment over P, right? So we have lots of atomic facts, and in a word, we just combine them together. Each fact is 0 or 1, right? So so if we combine this word together, we have a universe. Okay. And now we need to define another concept called accessibility. So for each agent A, we define a relationship. It's kind of a janked matrix, something like that. And if we write WRAV, that means, oh, from word W, agent A consider word V possible. Okay. So so now how we define belief? Belief is if agent A believes phi at word W, if and only if phi holds at every word V with WRAV. Okay, so this is kind of a little bit complex, but this is a really important concept in dynamic epistemic logic. Okay. So so now we need to introduce three concepts. The first concept is epistemic logic, and we have defined word, we have defined accessibility relationship, and we can also define a V. So V is kind of assignment to the atomic facts. That means which word satisfy each atom. Right. So if we combine these three parts together, this is epistemic logic. And a state is a pointed model. That means, oh, you have this epistemic model, and you have a word, right? So word, this W is the actual word. So so if we combine this M and W, now you have a pointed model. This is epistemic model. Okay, so now we need to introduce several representation. So what that means? That means we have epistemic model. We have word, a real word W, and entails P. And this happen only if W belongs to VP. Right. So that means VP means what is the corresponding word that can make this P true. So if W, if this word belongs to this kind of word, then we can write, oh, M and real word P can entail this P. Right. So we can only have, we can also introduce the belief operator in this process. Right. So MW entail BA phi if and only if for every V with this relation with this accessibility, MV entail phi. Right. So now we can have much more complex representation. So this is just one example, and we can have many, much higher order state of mind. Right? We can write be Tom, be Mary, be Alice, phi. That means Tom think Mary, think Alice, think blah blah blah. Right. So we can use this kind of framework to construct whatever high order state of mind task. Okay, so now we have a static epistemic logic, but this is epistemic model, but this is not enough because this is static, right? It can represent, which agent believe what is true in specific word, right? But this word is dynamic, right? And sometimes we have new events, right? So we need to represent how this kind of events drive the epistemic logic, right? So now we have an event model. So an event model formalizes an action, right? So first of all, we have a bunch of finite set of events. So this, for example, one is Mary moves chocolate to table, right? So this is one event, and we have lots of this kind of event. This kind form an overall E, right? And we need an kind of adjunct matrix. This matrix will tell us, which events each agent can or cannot distinguish. Right? Later we'll have example about this. And we have a precondition E. That means when may this event occur? And we have post condition E. That means how does the word change after this kind of action? Okay, so a pointed event model is an action, is the event that actually occurred. Right? For example, the event is Mary moved this chocolate to the box. So this action, right? So this is the event that actually occurred. And an agent who leaves the room cannot distinguish later events from nothing happening. Right? So this is how false belief arise. Okay, so given a state and an action with a precondition, we can define the third step. This is product update, right? That means we can use an action. We can apply an action to an epistemic state, and in that case, we will have a new epistemic state. Right. So now we can define, after this kind of operation, we have a new word, we have a new relationship, we have a new VP, right? So so now belief evolution is a deterministic operation on discrete structure, and now seems that we can modulate the whole process. Like first of all, we have some observation, and now something happened, and we have a new observation. We have new idea about beliefs, right? Okay, so here's an example. Okay, first of all, John and Mary and Alice enter the kitchen, and John put chocolate in the drawer, right? So now this is, let's say, state 2, right? At this state, everyone is in this kitchen, right? So everyone knows, actually, this chocolate is in the drawer, right? And now John exits the kitchen, and Mary moved the chocolate to the table. Okay, so now Mary and Alice are in the room, so they know, actually the chocolate is on the table, right? But John had left the kitchen, so John only know the old, unupdated place. This is the drawer, right? So and then Mary exit the kitchen, right? And Alice moved the chocolate to the cupboard. Okay, so now the Mary also exit the kitchen, so Mary's belief is also updated, right? So at stage 2, only Alice is actually is in the cupboard, right? So we can have this kind of process belief update, right? And now here's an example. We can use our DL derivation. For example, if we say 5 is chocolate on the table, right? So the question is, where does Mary think Alice think the chocolate is? So the real word is word 6, right? So it's M word 6, Intel, BM, BA, 5, right? Mary think, Alice think chocolate is on the table, right? So we can simplify this expression, and finally we can say, actually that's true. this part is true. That means chocolate, everything the chocolate is on the table. Great. Okay, so now we talk a lot about this kind of dynamic epistemic logic and some examples. Seems that it's really hard to understand, and now let's talk about the framework. Right, we have this kind of formal logic tool. How can we design a system that can ask LLM to give us better and verifiable human reasoning? Right. Okay, so the whole pipeline is like that. We have a generator. The generator is an LLM. So this LLM will propose multiple candidate belief traces, right? And we have a PBM. So this PBM is a verifier. This PBM will score each step against DL derived truth. So that means we will train a PBM using our formal logic system. And now with this PBM will judge the LLM generated result and will tell us, oh, this candidate is better, this candidate is not that good, right? So after we assign this kind of reward score, we can select the best result for next step reasoning, right? So that means, for example, we always have this question, right? Where does Mary think John think chocolate is? But at each theorem action, I mean, the story is kind of a set of actions, right? So, for example, at this stage, if we only observe stage 1 and stage 2, we don't know the remaining tasks, right? So we only know these 2 actions. So after these 2 actions, can you tell me where does Mary think John think the chocolate is, right? So this PBM will tell us, oh, most likely is in the drawer, right? We assign 0.99, right? So in that case, this let's use drawer as the next belief. Okay, so at stage 2, the result is drawer, right? So then when we have more actions, like we have stage 3, we have stage 4, we can have this kind of belief states based on the prior beliefs. Okay. So so this is how the whole process, how we use PBM to judge the generated result step by step. Okay. So now the problem is, well, how we train this PBM, right? How we train this PBM using our formal logic system, right? So the first thing is we integrate a formal logic system in a high-term generator. So high-term is a benchmark design for higher order mind reasoning, but in this framework, there's no formal logic trace tracker, and there's no way to get the intermediate result for the belief update. Okay, so now we integrate this kind of formal logic system into this generator, right? And now we can synthesize lots of story, right? Because we need to train a PBM. Okay, so for each synthesized story, we build an epistemic model at every state, and we update accessibility relations using even models for each action, and we record the belief state for every action and every belief order. And finally, we get about 20,000 stories, and each of them is like noise-free, and we have all of this per step symbolic label, like when this story roll out, what is the belief at each step, right? So now, seems that we have input. The input is the story. We have the output. The output is the per step label, right? We have true belief trace label, right? So by using this formal logic system, unlike human analyst or LLM as a judge, this kind of label are derived from formal logic and correct bound construction, and it's 100% correct, right? We can always use this to train a model. Okay, so this is how we train this process belief model. We use binary cross entropy, and we use GPT-4 Mini to generate reasoning traces, and we use the L golden model to judge, oh, this reasoning trace is correct or not, right? So by using this, we can train a process belief model. So this is actually a reward model, right? So this can be also used for reinforcement learning training, something like that, whatever you want. Okay, so we use a Llama 3.1 8 billion instruct as the base model. We trained one epoch, and it's down single GH200, and everything can be finished in 3 hours. Probably we can optimize this today, but yeah, at the time we just use the typical training methods and training infra. Okay, so now we have trained this process belief model. We need to do inference-time scaling, right? So how can we use this process belief model to work with our base LM? Right, so we have two methods for that. One is beam search. So this is in our previous slides, right? The figure is kind of beam search. So every time you maintain k partial belief traces, and at each action and propose B candidates, like B candidate next step update per beam, right? So we have k plus B multiply B partial pass. Right? So this PBM scores the new step in each pass, and we retain the top K pass based on the PBM score. That means this kind of partial belief are like highly reliable, given we have a powerful PBM, right? So so now in that case, error get pruned before they propagate to later steps, right? So it's like if we have an intermediate wrong step, this will be prompt. You want, we want to work based on this wrong intermediate step, right? Okay, so this is so this is beam search, and now we have another scaling method. This is best of n. So this is extremely simple, right? We can just ask this LM to sample n complete belief traces after reading the whole story, right? But they still need to give us step-by-step belief updates, right? And we can use this PBM to score every step in every trace, right? So we have a score for each step in this n traces, and we can aggregate this kind of step scores into a trace score. We have many ways to do that. We can take the score of the final step. We can use the score of the minimum score of the whole process. We can take average. We can take product of these scores. We can also just do a majority voting, right? We ignore the PBN, we just vote on the final answers. Right? And the result should, actually minimum and product is great, and majority barely helps. And we will show the result later. Okay, so for best of n, we have two different way. One is vanilla best of n, right? We can pick the single trace with the highest aggregated PBM score, right? We talk about how we get this score last page. We can also take a weighted best of n. Okay, so we can group trace by their final answer, then some PBM score in each group. And yeah, so we have two different best of one. And now let's talk about the experiment result. Okay, so the whole stuff is tested on Queen 3. Queen 3 0.6, 1.7, 4 billion, and 8 billion models. And we also test on Llama 3.2, 1 billion, 3 billion models. And this is for open source models. And we also test this on closed source models like GPT 4.1, GPT 4.1 mini, 4o, and 4o mini. So basically, these are best closed source model at that time. And we also show the result of some powerful closed source models like O4 mini, and we also showed the baseline result like 4.1 nano and powerful Queen 3 200 billion model, DeepSeek V3, and almost 32 billion. And we test on two data set. One is HiTom. This is high order belief track and consensus data set. This is a Henry and unexpected transfer scenarios. Basically, we believe this is kind of out of distribution, right? Because our PBM is trained on high tone-like questions, right? So everything is finished on a single NVIDIA GH200, and we use VRM for batch decoding. And the results show that after we use this kind of PBM, no matter it's BON setting, no matter it's beam search setting, we always have better result after we have this process belief model supervised. Yeah. So on llama 3.23 billion, we have 30 points, higher accuracy. And we can see even for closed source model like GPT-4 mini, we can also observe 18 points, better accuracy. Right. So now with this PBM, how's the result compared to powerful closed source models? Right. So by using Queen 3.4 billion with the PBM, the result is comparable to 235 billion model. Also from Queen 3, and it's better than GPT 4.1. So that means, with this PBM, with another small model, with this kind of formal system supervising training, we can have better result, even if the base model is extremely small. That means basically small models sometimes can give us really good result, but we have no idea. In the past, we have no verifier to judge, this one's great, this one's not great. Now with the PBM, we can have this kind of judgment. Okay, so this result show the effect of sampling budget. We show that after we have more traces, we can have better result. And we find that actually majority almost doesn't help. Right? That means we really need this kind of verifier, and basic majority voting doesn't help. Yeah, I think this is really interesting because there are lots of RL paper, lots of training paper try to claim that they do self-improving stuff by using majority voting, right? So they vote on some questions, and they assume this kind of voted result is pseudo label and use this pseudo label for training. And they claim, after this kind of training, we have better result, right? Seems that's not true in some scenario, right? Because in this kind of serial mind test, it seems that majority voting doesn't work. And I believe that in lots of scenarios, majority voting won't work. Majority voting will only solve the question that the base model can already solve it easily. Like you try twice, you try fourth time, then you can get correct answer, right? In that case, you do majority voting, it might help, but in other scenarios, seems that it's really hard. Okay, so best of n or beam search. Let's say the result is best of n is enough. Seems that beam search costs a lot. At the time, we don't have much support for SGLang, right? So in SGLang setting, maybe we can use beam search, and it's a little bit better because we can cache the prefix. But at the time when we use VRM, actually, it's really hard to do this kind of cache stuff. So seems that it costs a lot to do beam search because you need to rerun the result every time we get a new belief update, right? So seems that result for best of n is also really great. Let's just do best of n is enough. Yeah. Okay, so for out of distribution result, we also show that with our PBM, we can have a result on this kind of Henry and zero mind tasks. Right? So it also works. Right? So it's really interesting. That means we are not just overfitting to synthetic high-tone data. Okay, so we also showed that the capability of PBM is also really important. And we showed that if you have a bigger base model, you have a better PBM accuracy. And with the bigger and better PBM result, you can achieve better result. Right? That means you are using the same base model, you are judge the same reasoning traces, but if you have a good PBM, we can select the best result, and this result most likely is correct. Right? So we can achieve about 10% accuracy boost. Okay, so so now we have base model, right? So if we scale this base model, we can have better performance. But seems that in Queen 3, without this PBM, the results like that. Right, the results like that. I think we observed this in many other tasks. Seems like the Queen 3 ability is not trained that well, right? But after with the help of PBM, seems that we can have a more, a scaling trend that makes sense. Right? With bigger model, the results are always better after our PBM help. Okay, so another thing is, in that case, you need to have many rollouts, right? This costs a lot, right? And in that case, are you still better than just call a bigger model? And we show yes, that's true. Even if we call mini and PBM, right? We call this mini model for mini 4 times, and the result is still better than call GPT 4.1 and GPT-4 directly. N equals to 1, right? And the result is better and it's cheaper. Right? So in that case, and seems that we can just do this kind of test and scaling. That's fine, even if we are calling closed source API. Especially recently, this kind of API enable input prompt cache. Right? In that case, they charge less on this kind of input cache. Okay, so that means it's still good to just call a small model with test and scaling, even in a closed source API scenario. Okay, so so now is the conclusion. We reframe theorem reasoning as a verifiable multi-step belief update process, right? And first of all, we formalize this by using dynamic epistemic logic, right? So this gives me a calculable model of nested belief, and we train a lightweight PBM by using a DEL simulator, generate lots of data, right? So now we train on PBM, scores this kind of intermediate beliefs upstates, and then we do inference-time scaling, and we show it's really powerful. Okay, so in that case, the output of theorem of reasoning is no longer a guess at the label, right? It's a chain of belief states that has been independently verified. And let's say DL theorem is just an instance of a broader paradigm, right? Seems that we can use symbolic methods to generate lots of verifiable synthetic data, and we can use this data to train model, right? Then we will have a better neural reasoning in that case, right? So DL is a symbolic spine specific for belief dynamics. And the PBM is one product, it's noise-free supervision, and we embed this kind of supervision into verify, which can verify. And it seems that this framework generalized, right? Anywhere there's a symbolic simulator, there's a noise-free training data and a verifiable signal, right? So DL is one tool, right? Theorem is one domain. What about everyone else? Right? We can scale in this kind of symbolic tool stack. Right? For belief dynamic, we have DL, and for like agentic text, we have finished state machines. Right? And for temporal constraints, right, we have other model logic. Right? For arithmetic, we have Lean, something like that. Right? So so seems that we can build a library of symbolic simulator, and each produce diverse and verifiable training data, and then learn like we verify on top, right? So so this is one interesting point, right? So it's based on the generator and generation and verification pipeline. Okay, so another interesting question is, seems that we can ask agent to use this kind of tool at inference, right? So right now, this PBM observe the knowledge offline and training time distillation of a symbolic system, right? Maybe next step, we can also ask this agent to call symbolic tools at inference, right? And I think we are do that in many domains like mathematical reasoning, right? Yeah, but it's not applied to other this kind of model logic, something like that. Okay, yeah. So in that case, we can also ask this LM to propose a belief update and use the DEL solver to certify this, right? So in that case, this reasoning become interactive. It's kind of a agentic framework, right? This agent can we can make all of these solver as kind of tools, and yeah, and in that case, the app is no longer a self-contained oracle, but a participant in a hybrid neuro-symbolic loop. Yeah. Okay, so thank you so much for listening. I think the autonomous small statue neural reasoning grounded in symbolic supervision, and all code data and the PBM checkpoint can be found in this GitHub repo. And any questions?
All right. Thanks so much, Yuheng. We only have a little bit of time left for questions, but I have a question. But why don't you take a few from the audience, Olga?
Oh, we don't have any questions from the audience so far. So Alex, you can start with yours.
Okay. Yeah, I'm just wondering, in these synthetic stories, where, for example, what are the hard ones and what are the easy ones? Like, first of all, for your system, for the PBM, where does it tend to make mistakes qualitatively?
Okay, so you mean which kind of question is kind of simple, which question is hard?
Yeah.
Okay, so let me go back to the example. Okay, so in our high order Schumann task, the color question means you have, the belief is nested, right? We can ask many questions here. We can ask, where is the chocolate, right? This is the simplest zeros order question. This is simple. And we can have high order, right? Where does Mary think John think the chocolate is? This is a high order question. This high order question is hard, right? So we can have an intermediate difficulty question like, oh, where does John think the chocolate is, right? So when you have multi layer, you have high order question. This is hard, and this is not the only source of difficulty, right? We can also add lots of other stuff. Like in the original high tom task, there's some announcement, right? So this kind of people can just tell them a lie, right? Can lie to others, right? Oh, I think the chocolate is in blah blah blah. Right? So the other people can choose to believe it or not believe it. This will also affect the belief updates, right? So in that case, this is a more complex reasoning scenario. But actually, I believe this is also part of the. Let me think. Okay, so yeah. So I think somewhere here, right? Somewhere here, the kind Bartek or someone else also try to incorporate this kind of announcement in this dynamic epistemic logic, right? So let's say difficulty goes from 2 dimensions. One is a more comprehensive formal logic system, right? You have announcement. You can lie to others, this one. Another is you have high order stories, right? In that case, you have lots of agents and you need to do complex reasoning. And let's say, actually, this is just a toy example. It's not that hard. The paper is about your mind, that's fine. But let's say a belief in real world scenarios is much, much more complex. And obviously, this kind of simple solver can process this kind of complex story. And this story is somehow, this story is kind of cliche because every question is like this, right? This high tom simulator is more like you have some primitives, right? And with this primitive, you can encode lots of different name, different structure into the same story, right? So I think this might be a little bit stiff or not that dynamic, but we just want to show this kind of possibility, right? But in the future, of course, we need to make it more diverse and more realistic question.
I guess that's always a problem with LLM.
When you try to
what LLMs
when you
can
try
do.
to formalize something, right? You need to simplify.
Because if you have templatization in your generator, then the LM will just learn possibly a surface pattern.
But it's still kind of reasoning, right? But in a more realistic scenario, we should make it less template based. I think there are lots of paper about your mind reasoning benchmarks, like explore your mind and others. Seems that most of them based on templates, right? In that case, it's not verifiable because there are lots of ambiguity in this kind of socially aware agent tasks.
Alex, we do have one question from the audience.
Yep, go ahead.
Is it possible to fine-tune the reasoning of the models using PBM so that the models learn to reason correctly?
This is an extremely interesting question, and of course, yes, right? So in this paper, what we do is inference-time scaling, right? We don't change anything. We don't change the base model, but we do train a PBM. This is a model that can give you reward at every step, right? And in that case, you can do GPO, right? I mean, for GPO, you even don't need this kind of process level reward. You can just use the final reward, right? You can use other IR training methods. Of course, you can also just use sequence fine tuning, rejection fine tuning, whatever you want, as long as we have this reward signal, right? So basically, the main contribution of this paper is to propose this kind of reward model, and with this reward model, you can do whatever you want. And in the EMLP paper, we do discuss some other GRPO works. And at the time, I said, seems that for GRPO, we need lots of compute resources and something like that. But seems that after that, everyone's working on our training, this kind of stuff. And it's shown to be extremely powerful. Right? So in that case, seems that's really interested to embed our PBM into our training dynamics. I know several papers about this kind of IR training based on final output, right? Because in this existing benchmark, we do have the final reward signal, and seems that the result is not that good. Seems that this LM will learn to guess what is the correct answer. That's not good, right? Probably with our PBM, we can have a more detailed reward signal. In that case, we might force this agent to do theory of mind reasoning instead of just make a guess.
All right, very good. I have more questions, but we're out of time, so maybe another time Yuheng will connect. But very nice work. I want to encourage students, researchers out there, this theory of mind stuff, which you may not have heard of before, but I think it's very important. We want agents. I mean, it's almost a definition of AI, right? Per Stewart and Russell. But if you want agents, sorry, Russell and Norvig. If you want agents, you immediately have to think about theory of mind, or multiple agents in particular. I mean, even if there's only one other one, which is a human interacting with the computer agent. So it's not an obscure topic. it immediately comes up as soon as you start seriously thinking about a computer agent. So, and a lot more work needs to be done, as Yuheng showed. So, there are many harder versions. I think your larger picture is also really interesting of ways to go, and looking at the symbolic stack in general that we have. You could say a few more I would add to that stack, but we can come to that in the summer school later. But anyway, very nice, Yuheng, and everyone check out his work, and hopefully we'll see more to come. All right, thanks everyone.